Well, welcome to the E4S tutorial. It's my great pleasure to welcome you to the ECP annual meeting 2021. Today's topic for this tutorial is the extreme scale scientific software stack. My name is Samir Shende, and I am at the University of Oregon. My colleague Luc Perlance will be helping with this tutorial as well. And it's my great pleasure to also welcome David Rogers from Los Alamos National Laboratory and John Rood from NREL, who will be demonstrating the ECP tools. So I would like to first thank my colleagues in the Performance Research Laboratory, OSS at the University of Oregon, and other contributors from various laboratories and universities, without whose help this could not be possible. Really thank them for all their assistance and contributions to the E4S project. The key challenge that we face is that as our software gets more complex, it is getting harder to install tools and libraries correctly in an integrated and interoperable software stack. The E4S project aims to deliver better quality software with documentation, with support for testing, integration. You can think of it as a delivery vehicle for software. We have community policies that I'll briefly describe. We have a documentation portal, which is a single portal for all the E4S product information. We have a portfolio testing. We have a curated collection of software. We do quarterly releases. We have build caches that can help speed up the installation of software as much as 10 times. We have a turnkey stack. You can go to our webpage, e4s.io. We are also we have big plans, and we are looking at a strategy group which comprises of US agencies, industry, and international partners as well. So what is E4S? E4S is a curated software stack which is based on the SPAC package manager. We have binary build caches for bare metal installs for x86 64, PPC 64LE, ARch64, ARM64 platforms. And we have container images on Docker Hub and the E4S website of pre-built binaries of ECP software technology products. We have base images as well as full-featured containers, which supports GPUs. We have recipes for creating custom images from base images. We also have integration with GitLab for building the E4S images. And we have a validation test suite on GitHub. We also have a tool called an E4S container launcher, or E4S CL, to allow you to substitute an MPI in your application in the container with the system MPI running on the bare metal hardware if it's using the MPitch ABI application binary interface. We also have a VirtualBox image with support for container runtimes, including Docker, Singularity, Shifter, Charlie Cloud. And we have AWS and GCP images to deploy E4S. You can learn more about our project at the e4s.io webpage. Now, what is our goal for this tutorial? Well, none of us actually knows all of those things perfectly. So we are all going to learn together in this tutorial. We can start by signing up for an AWS instance by going to this webpage, e4s.io/tutorial. If you have not done this, please do this and reserve an instance. We have 8 CPU, 32 GB Xeon Platinum instances on AWS. And I would like to thank them for providing the research credits. And then you can just go to this web page, such as Tute032, if you have chosen the 32nd instance, .supercontainers.org, and then this port and name, and give your login password. And you may have to press the space bar a couple of times for the password prompt to arrive. and then just click on a README file and we'll go through these steps together. Now, what do we want people to do in this tutorial? We are going to start off with a Hello Numerical World. This is a BSSW tutorial example, which uses visit for visualization. We will look at containers for HPC. And yes, we will create a Docker container. We'll create a singularity container. We'll see how to use Shifter. We'll also do MPI-based builds. We'll look at a NAS parallel benchmark. We'll have a full build of a Trilinos application called Zoltan. And we'll actually use the E4S CL tool to replace the MPitch in the container with the vendor Intel MPI on the AWS instance. Then we'll look at a Pantheon demo, which David Rogers will show, which will show Ascent. It will have cinema visualization. We'll use Jupyter notebooks. We'll have naluwind demo. We'll use a SPAC build cache to build this ECP application. Yes, we'll build a full ECP application from the binary build cache. It uses Trilinos, it uses Cocos. We'll launch Tau performance system to view its performance. We'll even look at the output of this naluwind demo, which will run on this instance in ParaView. We'll look at container images on these sites, and we'll look at other AI ML tools that are bundled in E4S with Intel One API. The whole Intel One API is there in this image. And we'll look at PyTorch and TensorFlow as AI ML applications. So we'll do all of these today in the next couple of hours. And I'm hoping we'll get through all of these. Now, I highly encourage you to also attend the other tutorials that are associated with E4S. The first is the SPAC tutorial, using SPAC to accelerate developer workflows. It's on Friday, April 16th from 10 a.m. to 6 p.m. It's an all-day tutorial. We highly recommend it. And then the intro to containers for HPC, which will be held on Wednesday, April 14th from 1 p.m. to 2:30 p.m. Eastern Time. So we're going to do all of this. Now, if you're concerned about what we need to do, well, you can be rest assured that all you need is a web browser. You don't have to install any software. You do not need to have even X Windows or terminal installed on your system. You just need a web browser to be able to go first to this web page and then launch an instance by just going to this URL. And all we really need is for you to be able to launch a terminal and cut and paste commands from the README document. That's all. And we'll go through these steps together so you can try these steps. And I know this is quite a bit, and I'm hoping that we'll be able to cover all of this today in the time. So you are well aware of the three areas of ECP: application development, software technology, and hardware and integration. Well, we have over 70 unique software products in the software technology portfolio, and this is what we are focusing on in our E4S project. We work on products applications need now and into the future. We have a range of packages that are critical for HPC. For example, for MPI, which forms the backbone of HPC applications, we have MPitch and OpenMPI. In OpenMP, OpenACC, we have tools with LLVM. We have projects such as Solve and Proteus Tune that are leading the development of these standards. We have performance portability libraries. We have Cocos, Raja, we have LLVM, vendor compilers. We have performance evaluation tools, including PAPI, Tau, and HPC Toolkit. We have math libraries such as BLAS, sparse solvers. We have Trilinos, PETC, sundials. IO libraries such as HDF5, Adios, MPI-IO, data and visualization tools such as ParaView and Visit. And these products are then classified into software development kits, SDKs, which are then a delivery vehicle for the extreme scale scientific software stack. And we have packages from the ECP ST portfolio as well as non-ECP products But our goal is to deliver this using the SPAC package manager. And in case you are wondering about how we can add more tools to this, well, there are some community policies that we have developed, and we have released this in the version 1.0 release of the E4S. You can find this on our webpage. And here are community policies. There are 9 policies that are available right now, which were modeled from the XSDK community policies. And there is a great effort from the SDK team to develop these. Now, we have a SPAC-based distribution of the software technology and related products, and we have bundled them together in a curated release of E4S. Now, we've had several releases, and we are now on a quarterly release schedule. You can see that we started in October 2018 with 24 releases, and then we have grown from that, from 24 all the way to over 67 full release products, as well as the DOE fork of LLVM, which includes Clang 13 and Flang compilers. This was released in 2021 in February. And we use SPAC as the package manager for software delivery. SPAC provides the ability to specify versions of software packages that are and that are not interoperable. It's a build layer, not only for E4S software, but for also a large collection of software tools and libraries outside of E4S. And it supports achieving and maintaining interoperability between ST software packages. You can learn more about it at the spac.io webpage. And the motivation for that is that scientific software is getting extremely complex. Just the dependency of NALU, which is the generalized unstructured massively parallel low mark flow, it looks like this. You can see the large number of dependencies. And we will actually build naluwind and demonstrate it in this tutorial. Here's another code, deal2, which is a C++ finite element library. And you can see the dependency getting more and more complex. And here is RMiner, our data mining library. Even proprietary codes that are based on many open source libraries have a complex dependency graph. Now, over here, you see the Aries tool chain, and half of this DAG is external blue, and more than half of it is open source software, like all of these packages. And nearly all of it needs to be built specifically on HPC systems to get the best performance. And in the ECP, we are building an entire ecosystem of 15 applications or more with 80 software packages on multiple architectures and platforms with different compilers, with different programming models, and multiple versions of each package with external dependencies. So this adds up to a combinatorial explosion of the total number of packages that you may need. And every application has its own stack of dependencies. And it's become, it has led to a point where developers, users, and facilities are now dedicating many FTEs just to building and porting applications. And they often trade the reuse and usability for performance. So we must make it easier to rely on others' software. Now, how do we install software on a supercomputer? Well, first of all, we go about downloading all the 16 tarballs that we need, and then we start building. And it looks a little bit like this. We first configure, we type make, we fight with the compiler, we tweak CXX flags, we tweak CMake configurations, again, change the arguments, install, and then finally, when all these 16 packages are installed, then you get a binary for your application, and then you run it, and it may segfault. And so you go all the way back and start all over again. Now you may say, what about modules? Because some, in fact, most supercomputers deploy some form of environment modules. We have Pickle modules that date back to 95 and LMOD from TAC. which are very popular. So you can just say module load, and then you can run that software. But you need to remember that the modules don't install the software. Somebody else has already installed it. Modules merely set paths, LD library paths, path variables, and you still need to have someone install the packages. So SPAC is a flexible package manager for HPC. It has been adopted by ECP as the main delivery vehicle. You can easily install SPAC by just doing a git clone on this URL and then sourcing the setup.env, setup-env.sh file, and then you're ready to install a package. You can just say SPAC install tau, and it will install the tau performance system and its dependencies within the SPAC directory structure. But unlike typical package managers, SPAC can also install different variants of the same build. And you can have different compilers, different MPI implementations, even different build options. Well, how does it look? You can first clone the SPAC repo, set up your environment, and then I typically say SPAC compiler find. So it sets up the compilers. I can say SPAC external find. So it sets up external packages. You may not want to install packages like CMake, M4, and other packages like tar from the source code. You may just want to pick up the ones that are pre-installed on your system. So this is a very important step. Then you can go and install a package. You can say SPAC install tau, and it will install the unconstrained default version. But you can do better. You can say, oh, but I want tau version 2.30.1. And then you can give with the @ symbol a description of the version that you want. You can also specify compilers. Now, what is great about SPAC is that it understands different compilers, which are found in this step of SPAC compiler find. And you can specify a spec like this. You can say % for identifying a compiler, and then say GCC at the @ symbol for the version, and then 730. Or you could specify build options. Each package has some variants. In the case of tau, for Intel GPUs, it has the level 0 API support, and you can say tau install tau plus level 0, and then it will do that. Or you can say install tau with MPI, but please use mvaph2 with version 2.3, which was built without the wrapper RPath option. This wrapper RPath option, without that option, allows you to substitute the MPI from within the container with an external MPI. And so you can specify a great deal of detail with these specs. And the spec syntax is recursive. That's what makes it so interesting with SPAC. You can say SPAC find, and it will show you what was installed. So here I'm seeing, for example, on this Power 9 architecture, I see Trilinos version 13.0.0. Multiple versions can coexist. So you can have SuperLU dist version 630 as well as 631, and you can just load that package. And then you can generate module files automatically. So you could then say module load a package as well, or you could say SPAC load -r and SuperLU dist at 630, for instance. So in short, SPAC simplifies HPC software and is easy to use for users, developers, cluster installations, and the largest HPC facilities are now using SPAC. It is also central to ECP's software strategy, and it enables software reuse for developers and users. And it allows facilities to consume the entire ECP software stack. There are many interesting features in SPAC's roadmap. I encourage you to all go to the spac.io webpage and learn more about it. As I mentioned earlier, they also have a tutorial on Friday. Please plan to attend that full day tutorial to learn more about SPAC. Now, looking at our building of these packages using SPAC, the SDK or software development kits are central to our strategy. And we have a number of different areas, including workflows, which has been added to this list of different SDKs. And then within these SDKs, we have multiple packages, as you can see over here. And these packages are then built. We build it, we test it, we deploy it. It's all integrated. There are multiple SDKs that are comprising the E4S. So in short, to recap, E4S is a curated release of different E4S products based on the SPAC package manager. And we have support for both bare metal installs at facilities and also custom container builds. You can cherry pick different packages and start with a base image to create a custom image of a container. And then you can have multiple recipes. You can create your own recipe. You can create compact binary container images and then use E4SCL to launch these images. We also have a validation test suite, and we have a GitLab-based CI process. I'll describe all of these, but to start with, let's go to the basics of what are containers. Container is a lightweight collection of executable software that encapsulates everything needed to run a single specific task. What is important about containers is that it does not include the operating system kernel, and it's based on Linux. You can think of it as chroot on steroids. And it's widely used in industry. There are differences. You may have heard of hypervisors and containers. Okay, so there are type 1 hypervisors that insert a layer below the host operating system. There are type 2 hypervisors that work within the host OS, and then containers, where you can see that there is only the operating system of the host and their container-based operating systems without the kernel. So there is a missing piece here with containers, which is we use the same kernel from the host OS. Now we have many container images that we have released for different platforms. And if you go to the E4S.io webpage and go to the download link, you can find this. You can also do a Docker pull directly on an image. Here is an image for Ubuntu with CUDA ROCm, a PPC64LE version with CUDA. And we have just done a release of 2021.-02 GPU release for x86-64, which for the first time has support for 3 different GPU architectures. And yes, we support AMD ROCm as well as NVIDIA CUDA, as well as Intel One API. We have support for 67 different ECP products, as well as we have AI and ML packages. We have support for TensorFlow, PyTorch, Horowod, with support for GPUs. So installing these packages can be non-trivial. We have taken care of all that and created a curated release. You can see different packages and where they're installed in the image. For example, this is the location of Dynast API, or Cocos, or Hyper, or Magma, Mercury, MPage. You can see packages like PETC, or Parallel Net CDF, or Jupyter Hub. We have Sundials, SuperLU, Tau, Trilinos, Umpire, many different products that you can see over here. We also have Singularity images. Singularity is very popular as a container runtime, and you can just download this image, a single file, and you can just run that image with support for One API, CUDA, and ROCm. And you can, of course, get these releases from Docker Hub. Here are examples with, say, PPC64LE and x86-64. And yes, we have 67 different products for the IBM Power 9 PPC64LE platform as well. In case you're using systems like Summit, you can look at Singularity images. You can look at containers. Here are packages installed in different directories for Power PC, PPC64LE. And you can see Magma, MPage, Adios 2, PDT, PETC, SuperLU, many different packages for PPC64LE. And you can download a PPC64LE Singularity image as well. If you are running on an IBM system with support for, say, GPUs, you may want to add the --, NV flag so that it pulls in the CUDA libraries from the host. So you can say singularity exec dash dash NV and so on. Now it has support for GPUs, and here is an example of a Power 9 session. I've just said singularity exec dash dash NV. I can launch Python and say TensorFlow, import PyTorch, CV2, OpenCV, Matplotlib, NumPy. All of those commonly used Python tools and libraries are now in your path. So you don't have to do anything special to create a version of, say, TensorFlow that can access the GPUs. You can see over here, test is GPU available, and it finds the 4 V100 GPUs, Tesla over here. And we also have base container images for different operating systems that you can download from Docker Hub. We have multi-platform E4S Docker recipes, and we show exactly how to build it. This is a Docker recipe which says start with the Ubuntu 18.04 SPAC x86-64 image, and then this is the work directory. Copy this spac.yaml file. For those who are not familiar with SPAC, there is a spac.yaml file which lists all the packages and dependencies and encapsulates your entire environment, so to say. So then you can just say SPAC install and then create the Docker image. And then there are Docker images for recipes for different platforms. Here is an example for x86-64, PPC-64LE, and AR64. And this is how a spac.yaml file looks like, where we can say, this is the full build of E4S, and it has different versions of, say, Trilinos, MFEM, Hyper, and you can say Docker build, and then this with the dot file. And then if this spac.yaml file is in that current directory and the Docker file is in the current directory, it will just use that and create the Docker application. We will see how to build a Docker container. You can also do a bare metal install by just having this spac.yaml file. You can just say spac, use the environment in the current directory with a -e dot, and then install it. And it will take this manifest and it will build all these packages in an optimized manner. Now, you can speed up the installs by using a build cache. What is a build cache? It's a collection of SPAC binaries, that's all. For different architectures, for different operating systems, you can see that right now we have over 37,000 binaries. If I click on this Amrex at 2103, I can see specs for different architectures such as PPC-64LE or x86-64. I can see the operating system over here and the compiler used to build it and the unique hash that has to match. So if you have the architecture, OS, and compiler that matches your these 3 parameters, you will get this hash, and then it will be able to download the exact binary. If it is a different compiler, for example, on RHEL 8, you were using GCC 930, and we don't have a binary for that, then it will build it from scratch from the source code. There are other applications that are already beginning to use this. Here is the build for the whole device model application WDM app, which allows you to just point to the build cache at the University of Oregon, just to trust that key, and then add this mirror of E4S, and then just say SPAC install, and it will use the binaries from here. This can help speed up your installation. The Pantheon project at Los Alamos is using this. They have reported approximately 10x speed up in building their applications by using the SPAC binary build cache. We'll learn more about it, and David will show a demo of Ascent and Pantheon tools, and you will be able to follow along and actually run the Pantheon app all on the EC2 instance. We'll also show a demo of the naluwind application, and John Rood will guide us through this. He'll have a set of slides that he'll present. And this is an incompressible flow, computational fluid dynamics code used for wind turbine modeling. for near body solvers, and you can see the airflow effects. And he'll describe it, of course. And this is the URL for the Exawind repo. And we'll actually run this test case all on the EC2 instance. I'm hoping that everything will go without a glitch, and we'll be able to all visualize this unique data set in 3D using ParaView on the instance that you have. Now, it's not enough just to install a set of packages. We also need to validate that they are doing the right thing. And how do we do that? Well, we have two projects. One is the SPAC test framework, and it allows you to embed in the SPAC recipe the testing commands. We also have an external testing framework called the E4S validation test suite, which can sweep across a set of packages that are pre-installed in an image before releasing it for validation testing. And what does that look like? Well, there are several directories in this test suite. Here is a validation tests for Magma. And you can see that there are scripts in every folder which have clean.sh, compile.sh, setup.sh, and of course, run.sh. We actually compile the code, we run it and validate the results. And then we get a pass or fail indication. And this is really important for releasing a curated set of packages. You can find out more about the E4S validation test suite at this URL. Now we have container builds, reproducible container builds using E4S base images. And here is a Docker recipe. And then this is the spag.yaml file. And you can see over here that if you don't want to bring in all 67 different packages, you could start with something like this and say, look, I want to create an optimized container. I don't want everything. I just want super LU dist. I want PETC, MFEM, Strumpack, Butterfly Pack, and OpenBLAS, and nothing else. And please start with this base image from ECP E4S and then build this. Now, what do these base images have? They have support for MPI. They have support for compilers, so you don't have to create those from scratch. They have support for MPI that will permit you to replace the MPI with the system MPI. And it understands GPUs. You may find people complaining that when they create a base image from scratch, from say CentOS or Ubuntu, and put packages, it's hard for these images to recognize a GPU. Whereas container images that you download from a vendor platform like the NVIDIA cloud platform, they have support for these GPUs. So what is missing? Well, we have figured out exactly what we need to do to support all different GPUs, whether they are from Intel, NVIDIA, or AMD. And we have that support in these base images so that if you use one of E4S base images and then create your custom image, you will have the ability to access the GPUs and do the replacement of MPI, because there are some special flags that are needed. Here are examples of images which are just bare bones images, as well as images that you can use for GitLab runners. And you can see all of these images and how many times people have downloaded these. We also have a integration with GitLab. And here is an example of what we use internally at the University of Oregon for the E4S builds. You can see these different pipelines, CI/CD pipelines for different operating systems, different architectures, and then these are the pass and fail results. Now we also have GPU runners on Frank, the set of systems at the University of Oregon that includes support for all 3 GPUs from different vendors, including A100, DG1 from Intel, MI50 from AMD. And we would like to thank the vendors for their support of Frank. And this is a platform that can be used for GitLab runner instances. So here is a multi-stage E4S CI build pipeline. This is at Cori, at NERSC, and you can see the E4S build pipelines where they are creating binaries through GitLab. This is the build cache at Oak Ridge National Labs on Ascent. This is for the PPC64 LE platform. You can think of Ascent as a platform that mirrors the big Summit system. And you can see how they are building images in their own GitLab build pipeline for E4S. And these are facility specific builds. We also have CI badges for the E4S, which are now available at this GitHub site. And this is work from Berkeley Lab. And then we have a doc portal, which is a single online location for accurate product description for the ECP software products. And you can find more information about this. We rake the repositories for different products and then extract information from them for things such as the README files, the change log, and other product specific information. Different products can customize this by creating a .e4s directory and having a file that our doc portal reader can access. So you can just make a special directory, such as tau has a .e4s directory where it specifies the location, the mappings with the README file, the change log, etc. And then you can search for this over here and then find the name and area over here. We also have a VirtualBox image, which has these different HPC runtimes. So you could just install an image on your own laptop and learn more about different container runtimes, such as Docker, Singularity, Shifter, Charlie Cloud. It also has SPAC installed in it, and then you can just run a local image of E4S. Finally, I would like to mention this tool called E4S CL, which is a tool to simplify the launch of MPI jobs in E4S containers. And we have the support to replace an MPI library using the MPitch ABI compatibility layer. Now, if you try to do this yourself to replace the MPI, you'll have to parse a large number of files. In some cases, you may actually have to run the code, then see the output of that code to see which directories were accessed, which files were read at runtime to get that full list. And it's a cumbersome process. It also makes the launch of these MPI jobs very cumbersome if you're trying to use a container which has MPI in it, but you want to substitute it for a good reason with the system MPI, because the system MPI may deploy libraries that can access the fast network interconnect, such as the Mellanox InfiniBand, and then you may want to use a vendor supplied MPI library. So you can still build your application in the container using all those libraries, and then just substitute at runtime the MPI layer. Now we have made it simple enough so that you can just say E4S CL init, and then E4S CL launch with the MPI run command. This is a very interesting project. We are trying to now go beyond just the MPitch ABI compatibility layer and even target OpenMPI with the PMIX set of libraries, and you can learn more about it here. We are going to use this in the hands-on to replace the MPI in your application with the Intel MPI from one API. And this is the architecture of it, where you can capture all the dependency information, store it in a database, and then you can launch the job using E4S CL with the launcher command. So, well, in summary, what is E4S and what is it not? Well, E4S is an extensible open architecture software ecosystem which accepts contributions from US and international teams. It is not a closed system that only takes contributions from DOE software development teams. You can think of E4S as a framework for collaborative open source product integration. It is definitely not a monolithic leave it or take it software behemoth or a commercial product or just a simple packaging of existing software. Rather, you can think of it as a full collection of compatible software capabilities and a manifest of a la carte selectable software capabilities. You can think of it as a vehicle for delivering high quality, reusable software products in collaboration with others, and really a conduit for future leading edge HPC software targeting scalable next generation computing platforms, a hierarchical software framework to enhance via SDKs software interoperability and quality expectations. We are still working on a number of issues. We are improving support for GPUs, visualization tools. We are doing work with DOE LLVM, integration with that, CI testing, facility deployment, improving the startup of MPI applications. We are looking at source-based builds assisted by binary build caches, and we have container images for Docker Singularity that are available for download from this web page. Our future vision is something like this. It has E4S has now emerged as a new top-level component in the DOE HPC community, and this helps us enable new relationships. We have potential for new interactions with other US agencies, US industry, and international collaborators. NSF and the UK are examples. We have a portfolio that can expand to include new domains. We are already supporting machine learning and artificial intelligence packages. You've seen examples of these with TensorFlow, PyTorch, Horoward. Looking at lower level operating system components, our goal is to provide better, faster, and cheaper product capabilities. A lot of this work goes on at the Performance Research Laboratory at the University of Oregon. And we have an active visitor program in other times, of course. I'll show a demo of Tau as well, and these are support acknowledgements for Tau. We thank our sponsors for their support, especially the Exascale Computing Project for their sponsorship of the E4S project. Now, in the hands-on session, I request you to all go to this URL e4s.io/tutorial. I'll just e4s.io/tutorial. And there you'll find a set of these EC2 instances. Please reserve an instance by putting down your name and email address in the table, and that instance will be reserved for you. We have plenty of instances. Even if more people join us, everyone can have an instance. Here is the login, and here is the password. So please go to an instance on a web browser like Tute032 if you have reserved an instance number 32. And here is the login, here is the password. Then please press the space bar maybe multiple times until you are prompted to enter your password. Open a terminal window, click on the readme.txt, and then you will be able to use this. And with this, I will go on to the hands-on session and talk about containers first, and then David will present the slides on Pantheon. But here is, I see the sign-up sheet, and we have many people who have signed up. I'll just wait for everyone to sign up. And really, you can do this hands-on session. It only requires you to cut and paste certain commands. I'll take a brief moment to see if anyone has any questions, and please feel free to unmute yourself and ask if you would like. Well, in that case, I will go to the sorry. So I have gone to the tutorial web page, and I have reserved the instance called Tute001. And this is the DCV software. I'm using tut001.supercontainers.org:8443, the port number /#E4S. Now, I see a login screen like this. You should all have something similar. And then all you need to do is say tutorial and give the password. I'll put these instructions back over here. You first go to this tutorial page, reserve an instance, go to this web page, give the login and password. And it is HPC Linux 12 exclamation, and then click login. Now here, you may have to press the space bar a couple of times to get the prompt for the password again, and then again press HPC Linux 12 exclamation. Now with this, you should have an instance. Now first, you can just put these icons so that you can double click on this readme.txt file. You can see the terminal icon, the Firefox icon. I just need one. And of course, you'll see that the slides that I just presented today are all there in this E4S.pdf document viewer. So if you wanted to cut and paste anything, for example, go down to the last set of slides, they're all here, like so. Okay, so I'm gonna cut this. And then I'll just go to the GNOME terminal. Now here, let me just increase the size of this font, maybe a little more. Okay, so all we need to do is to follow the README file for this tutorial, okay? And we have made it simple that all you need to do is just, copy and paste. Now, I can use a double a mouse by just clicking this, and I'll just go here and paste it over there. So I've gone to the SRC demo, hello numerical world example, and this is the URL for this. I can open this URL in Firefox, and it's a heat transfer equation solver application. This is the hello world, a numerical hello world example. Okay, so I can click the Firefox and open this. All you need to do is say first make clean over here. In fact, if you click this XSDK project F, it does take you to this specific URL, which describes this heat transfer application. This is the full application, hand-coded heat transfer. It implements a simple numerical algorithm, use it to solve a simple science problem. And let me just close this Firefox second thing. So all I do is type make clean over here like this. There are no binaries. I can say make check all, and then finally just make. It solves this heat transfer equation, and then it runs it in with different algorithms, and then you can say make. And let's look at the application over here. So here you can see the problem of heat transfer. And there's a question a person is asking. He says that, well, there's a water pipe that's going through my wall. And will the pipe freeze if the temperature drops? And when I type the make, it runs the application, it solves the set of equations, the differential equations, and then it even plots this in visit. So the gist of this application is that here is the temperature. You can see the temperature dropped from 290 to 80 to the 273 Kelvin water freezing temperature, and then the distance in meters of the wall. And then you can see that if the temperature goes below the freezing point, the water pipes will freeze. Okay, so the question is, you keep the inside temperature of your house always at 70 degrees Fahrenheit, but there's an overnight storm coming, the outside temperature is expected to drop to 40 degrees below zero in Fahrenheit for 15.5 hours. Will your water pipes freeze before the storm is over? And then these are the governing equations. You can see that del U by del T, the PDE, simplifies to this one-dimensional heat equation, which is alpha with the second derivative of U with respect to X. And then there's a discretization step that happens. And then we can approximate the second derivative of U with respect to space X and form this equation. Then we can create this by rearranging the terms. And this is the final equation. And then here is the numerical treatment that feels like a mesh. And this is the FTCS algorithm. And here are the constants and the variables. And you are solving this equation. You can say make heat or make, and then you can see the output. Here is the default heat equation solver and the initial condition. And then you can see the results. Now it's important to visualize these results. And we saw that through the visualizer from visit. And then here are the constants for the wood, the brick. And then we look at this plot that just showed up after solving this. And then it helps us see that if the thickness is about 0.2, then what is the chance that it will reach this freezing point? And the answer is, will the pipes freeze? And the answer is no, because it will be above that. So here is the whole application. All you need to do is just go here to this numerical world and type make clean, make check all, make, and you'll get that visit plot, which will show up. And that's the first part of the Hello Numerical world. You can see the different files over here. And there's the FTCS.C, where you have the update solution FTCS. And these are the constants. These are the variables. And then you're solving this equation right here, the update algorithm using FTCS. And they are the boundary conditions. And then you can see that it's taking the UKI is based on the I+1, I, and I-1 based on this difference equation solution. And then you enforce these boundary conditions. So this is a simple example. It does not use MPI. It's just using a numerical solution, but it uses visit to plot the chart. And please go to this web page and see the full science behind this application. So now we have, at ground, just the starting point, we have a simple numerical solver. Now we want to take the next step in packaging of these tools. So let's look at different HPC container runtimes next. I'll wait for a minute for everyone to just be able to go to this directory, type make clean, make check all, and just pretty much just copy and paste from this README file into a terminal window over here. The entire tutorial will demonstrate a set of concepts, but it's really important for you to try these commands yourself and get familiar. We'll go from the very basics. We'll start with the first principles. We'll start with a hello world Docker image. We'll see how to run a different container. Okay, so I'll wait for a minute, see. Okay. Are there any questions with accessing the AWS? Are you all able to launch this web page by going here, opening up this? I know some of you would prefer to just watch, and I'm happy to demonstrate all the steps, but I really encourage you to just launch this and we'll all learn together. Okay, so let's start with Docker. Now, let me recap with what I said about containers. And you see, Docker container is a lightweight collection of executable software that encapsulates everything that's needed to run a single specific task, but it does not come with the operating system kernel. You're using the same kernel on the host. Now, in this machine, this instance that I have LS CPU. I have 8 cores of Intel Xeon Platinum. This CPU running at 2.5 gigahertz. What is the operating system name? You can see this is the Amazon Linux 2 on AWS. And this is the kernel 4.14225. Okay. So here I'm going to go to my home directory. I'm just going to say Docker images. Let me see what images I have. So I have an image for the stack tutorial. I have hello MPI. I have a simple image for Ubuntu. This is a 1404. Okay. Now I'm running Amazon Linux 2, but I want to run this image called Ubuntu 1404. And how do I do it? I can just cut and paste this command. I say docker run with the --rm so that it deletes it after the image is no longer running. And interactive mode, there's the tag here, and I just cut and paste this. I can also mount with the -v flag directories from the home directory into the Docker container. So I'm now launching the Docker container called Ubuntu 1404. And there it is. Now I'm inside the container, I'm root. Well, I can check the OS release. And here, it's no longer running Amazon Linux 2, it's running Ubuntu 1404 LTS. Okay. But if I see the kernel, it is still running the same 14.14 Amazon 2 Linux kernel. So Docker containers have the same kernel as the base operating system. And that gives them the performance. And you don't have to look at virtualization solutions. You are still running your entire software stack within a container. I'm coming out of this and I'm back on the base operating system, and I can say etc OS release. It will be different from Ubuntu 1404. It is now Amazon Linux 2. So you see, we just entered into this container by simply saying docker run like this. If I want to run Singularity, it's in my path. In fact, we have Shifter, Singularity, Charlie Cloud all installed in this AWS image of E4S. I can simply say Singularity run and then an image. So here is an image called LOL cow, which shows a cow and says something funny. Each time there's a different message. So I don't know what it will say now, but let's see. So I say Singularity run and the Singularity image. And it's a fairly standard, simple container. And from Mark Twain, The Innocents Abroad, it says, I must have a prodigious quantity of mind. It takes me as much as a week sometimes to make it up. So here you can all run this lolcow.simg. I hope you are able to do that. perfect day for scrubbing the floor and other exciting things. Okay, so that's running the Singularity container over here. And now I'll take you to the next step, which is building a Docker and Singularity container. And to do that, we will go to this directory and just cat the README file over there. I'll wait for a minute for people to catch up. The steps are right here. I recap. We first went to the numerical world solver, CD to that, make clean, make check all, go to this web page. You should all see a pop-up screen of visit show up with the graph. And then Docker images, run this Docker image, run the Singularity image, and here is the containers. How do I create a Docker container? How do I run it? So first, let me just look at this README file over here. You know what? I'll start another terminal so I can have a CD to this, and I'll CD over here. I'll cat the README file over there. I suggest you do the same. Just go to this CD src demo containers and just cat the README file. Okay. So here is the Docker file. This tells you how to build an image. Now, I highly recommend that you please attend the tutorial on containers for HPC. So I have a question here. It says, when you started a Docker, how do I get a Singularity prompt? I will show that with this container image. Okay, so here, let's first start with just creating this Docker file recipe into a real container. So I'm saying from NERSC Ubuntu MPI 1404, and here is a hello world.c application. Here I'm just doing an MPI init, MPI finalize, and I'm doing a MPI com rank, getting the rank, and doing a print statement saying, after you get the host name, hello world from, this rank out of so many ranks, so like rank 3 out of 5 on this host, and then do a barrier and then exit. So this is a simple MPI application. I want to compile this, put it into a Docker container, and then run it. And how do I do that? This is the step. I put a Docker file. It says start from the base image, add this hello world.c, CD to this app directory, and then compile it using MPI-CC, which would be in my path from this MPI image, and then create an application binary called app hello. That's all. So this Docker file, if it's in your current directory and I say Docker build, then it will build the hello MPI latest. And I do this by issuing the command docker build. So again, just copy and paste. You don't have to do anything special. Just say docker build, give it a tag, and say dot. So it knows that it must read the Docker file from that directory. It has created this. You can say docker images, and you'll see this image called hello MPI latest. Okay. And now you can say docker run. And again, I'm specifying the --rm flag, so don't erase it after it's done. This is the interactive mode. The tag is hello MPI and then the latest. So now I'm in this directory. Now you can recall that the Docker file put the hello application, in the app hello directory, right? So in the app directory, there must be a hello file in the app. And there it is, hello is the executable. So I can take this command and say MPI run -np4 app hello. And then it does get the answer from this app hello world.c. So I was able to compile this application, create a binary, inject it into the container. This is the hello binary. I was able to run the Docker container. I was able to just go in there and say MPI run on 4, and I get the hello world output. Okay, if you wanted to publish this container that we just built, if you have a account on Docker Hub, you can say Docker login with your user ID, and then you give your password, and then you can say Docker push, and then the hello MPI latest, and then in your area, dockerhub.com will have this image, and you can choose to make it private or public. And if you made it public, somebody else could go there with your login ID / Docker image. They could do a pull from there. So you are doing a push, they could do a pull, and that's how you publish your simple Docker container. This is a simple MPI application, hello world. This just shows you how to run a Docker image. The next thing is you can come out of this. You can see here, etc OS release. I am in Ubuntu 14.04. I'm still running the same kernel, 4.14 in the Amazon 2. And then I'm exiting. So now I'm back on my host system. Now I can do the same thing and create a singularity container. A singularity container requires, similar to Docker file, there is a definition file, and that is over here called Ubuntu mpi.def. Here I am pulling from the NERSC Ubuntu image and then running this run script. And this should just print a message saying, this is what happens when you run the container. Nothing special. This is just a bootstrapping from Docker, getting this image, and it's running over here. So to do that, I have these steps. I need to be root. Now remember, you can become root by just putting that HPC Linux 1.2 password, the password that we showed at the very end. This is the password. So you can say sudo bash, like so. Sudo bash. Now I'm root. As soon as I enter this password, and then I can say, this is the Ubuntu mpi.def file. And I want to build this by saying singularity build. Just like we did Docker build, now I'm doing singularity build. And it says, do you want to overwrite the image because it already exists? And I say yes. And it's starting the build process. Now it will build it, and it will create the singularity image. Okay. So with this, we have covered what a Docker container can do, what a singularity container can do. How do I build a Docker container? How do I build a singularity container? I recap, just go to this directory called src demo containers, cat the README file, put it in a different terminal maybe, so you can cut and paste, and just cat the Docker file, issue the command docker build, run it, run the MPI application, exit from there, and then start the Ubuntu. Remember to exit from the Docker container, to exit from there. The same way, now I'm root, but I have created this Ubuntu mpi.sif. I can exit from the root prompt so that I am now back to tutorial as a user ID. I have created the container. It's called, the container is Ubuntu mpi.sif for singularity image format. And I can just say this, singularity run, and then it will run this, and you are inside the container. So I'll take a couple of minutes for you to catch up and go through these steps. Yes, if you say just singularity run, the prompt changes. And thank you very much for everyone helping out in the chat with the questions that are streaming in. I hope you are able to do these steps. It just requires you to go to this demo containers directory, cat this README file, and just try these docker build, docker run, and mpi run commands. Then create this with sudo bash, enter your password, which is this. Do the singularity build, exit from the bash. Again, as root, you exit from there, and then say singularity run. And then once you are done with this, you can then close this terminal, extra terminal for the README file, and then continue with our other instructions. But did this work for most of the people?
Yes.
Any comments? It worked?
Yeah.
Okay, good. And the environment is stable, right? You are able to log in and there are no problems with EC2? Okay, no problems, good. So here I go back to my home directory, and then let me just close this terminal where we saw the Docker and Singularity, and then continue on. Here is the shifter. So we saw Docker, we saw Singularity. Now we look at shifter. Shifter has two different commands. There's the first command, which is shifter img to look at the images. And I can execute it like this, shifter img images. I can see that there's the Ubuntu 14.04 image. We chose this because it's a small, lightweight image, which has a different operating system. There's a BusyBox latest. Then I can just say shifter -- image like this. And now I will be inside the container. Shifter is another very good container runtime. Berkeley Lab has contributed to building this shifter container runtime. Here is the OS release. And now you can see I am in Ubuntu 14.04. So I can then be in this, again, as all the containers go, we are still using the same kernel. Note we are in the Amazon 2 14.14 kernel. And we are just using shifter to go to a different OS where your application may be packaged. And then you could run the application from shifter. So this shows us how we can use simple lightweight containers like the Ubuntu 14.04. What if I wanted to build a full application and I wanted a full featured container? Say the container that I showed with 67 different products. I showed you earlier that we have containers that are full featured where I can look at, here are all these different applications. What if I wanted to use these containers with support for all of these different runtimes? Well, I can just say singularity run and the SIMG file like that. So I'll just say ecp.simg and then hit enter. And now I will be able to look at this container and see all of these packages. SPAC will be in my path. I'll be able to check. I'm going to try and build an application. You see, this is the singularity prompt. ROCm is installed in opt ROCm. I have NVIDIA. I can say SPAC find CUDA, and then I'll see that we have CUDA 11 as well as 10.2, which I can load with SPAC load CUDA at this. I have opt ROCm where I have all of these packages. You can see the HIP compilers. I have opt Intel 1 API over here as well. So I have all of these 3 different Intel, AMD, and NVIDIA GPU support all in one image within the Singularity image. Now I'm going to just go to a simple NAS parallel benchmark, and I say CD to this, like over here, and then I will just say make clean. Now, mind you, if I say which MPI CC, I'm within the container. I'm in the Singularity container, and this is the MPI built with SPAC that I will use. So when I say make suite, as it shows over here, it will then use the MPI CC from this container. And now I'm compiling this. Okay, now I have built this lu.4.w. Let me go to the bin directory, like over here, and then run this command using MPI run. So I'll say run on 4 MPI ranks lu.w.4, and it ran it. It ran it in 1.41 seconds, and it says it's successful. So now I'm able to compile and run an MPI application. Okay. Now I have another example. This is called the Trilinos example of Zoltan. Let me just go to this Zoltan. I'm already in the container, so I don't need to do this ecp.simg run step. Okay. And now, if you wanted to exit, of course, you could say exit and you would be back on the prompt. But what I want to show is that I can take this Zoltan application. Okay. I can say clean.sh. It'll remove the binaries. I can say compile.sh, and it is setting an environment variable called Trilinos from loading up from SPAC location, and then it will compile it. Now it's using a number of libraries to create this Zoltan application. Just like I did with the NAS parallel benchmark, I can run the Zoltan application as well. Well, how many libraries does this binary have? I look at the size of the Zoltan, it's just 165 kilobytes. That's hardly anything. If I say SPAC load minus R Trilinos, I'm loading up the Trilinos and all the dependencies of Trilinos recursively using this -R flag. If I just say LDD Zoltan, it will show me which binary, which shared objects are loaded. And that's quite a few. All of these libraries from Trilinos are loaded. It needs all these libraries like libtucos remainder.so.13. How many libraries am I talking about? If I say LDD Zoltan, there are 47 different libraries that are loaded right here in this binary. Now let me just come out of here. And let's say I have this binary. I'm in the Zoltan directory, Zoltan. If I say LDD Zoltan, it says, oh, wait a minute, I didn't find any of these libraries. Why? Because all those libraries are in that Singularity container. Now, I want to run Zoltan on this machine, on this AWS EC2 instance. But I have got Intel compilers. I have got Intel MPI. I did not use Intel MPI to build Zoltan. I used mpitch. This is where the E4S container launch tool comes in. I want to take the binary, unmodified binary, figure out which libraries I need to preload to use Intel MPI, and then pull in all the other libraries that are required for Zoltan application. I can create a source, a file, and I can say run E4SCL.sh. Now here you can see there is a source.sh file which says, please load the Trilinos, load up the SPAC, load up Trilinos when you launch the container. But all I'm saying here is use the Intel compilers first. So that put it in my path by sourcing this set vars. Then do E4SCL init, specify which HPC container runtime you want to use, which is Singularity. Specify the image, specify the location of the startup script, verify that you are using the Intel MPI, and then launch the MPI run command using E4S container launcher. Then I'll just delete all this in the profile. So all I have to do is cd to this directory and say run E4S cl.sh. It will do all these steps for you, and it will replace the MPI in the application with the Intel MPI. It's doing this part. It figured out that there were 10 libraries that were relevant, that these files, it has put it in the profile, and there, it's running the application now. And it passed. So here, it ran the Zoltan application, and it loaded the 47 different libraries, and it was able to use the Intel MPI. Do you see the which MPI run command shows that it was using opt Intel 1 API, MPI, bin MPI run. So it's using the system MPI with the container which used Trilinos, which was built with the mpich libraries, and then substituted the MPI at runtime using the mpich ABI compatibility layer. So this is a tool that we have developed in the E4S project. Jean-Baptiste Skutnik from our team has devoted considerable time in developing this tool, and it allows you to do this MPI replacement. Very soon, the next release of this tool will feature interoperability with OpenMPI as well, where we will be able to use PMIX to do the translation of these calls at runtime. So to recap, start your container with Singularity run ecp.simg in the home directory, go to the Zoltan directory, compile, clean, exit from there, go to this directory, cat this run file, and just run this command. I'll take a few minutes to see if everyone is able to do these steps. Again, all we are doing is following the script in the readme.txt file, nothing special, just launching a terminal, running through these commands. Does it require MPI run to work? A question from Robert Blake. What if you are using something else to launch MPI jobs? So it does not require MPI run. We have support for Slurm and other launchers as well. Does that answer your question? Having Trilinos set up in a few seconds is great. Will we see how to get 4x speed up when we use 4 MPI ranks today? Well, you can certainly launch the applications, whether it's NAS parallel benchmark or others, and see what kind of speed up you get. And if you don't see a good speed up, we have tools such as the Tau performance system that can show you where it's spending its time. In fact, we can do that in the naluwind example, and we hope to do that. The E4S CL documentation suggests that it required MPI run, so I wanted to ask. Well, we do have plans to support a number of different Slurm-based runtimes. If we don't have it yet, we can be sure that it will be coming in the future. But I hope this is working for everyone. I wonder the performance deterioration when we use containers. So in fact, it's an interesting question. They have, with Python-based workflows, they have actually found that because with a container, you are using the RAM for the file system, you don't need to go out to the metadata server, which is associated with, say, Lustre on a large file system. So for HPC workloads that use Python, which load a lot of shared objects at the same time, you can find that the startup phase with containers can be, in fact, even faster. And of course, there are some slowdowns that you may encounter, but most people have reported that for a tuned execution, the use of containers does not pose a problem. I would encourage you again, as I said, to attend this very special tutorial that is planned on Wednesday, April 14th from 1 p.m. to 2:30 p.m. Eastern Time on Intro to Containers for HPC. And Andrew Young, Shane Cannon, they'll be there to answer the questions on scalability with containers. So that's a very relevant question. And I would encourage you all to go and attend this Intro to Containers for HPC and look at various options. Now, you can yourself try it out in this environment, compile your application with container, without the container, see how much time it takes, and see if you're looking at slowdowns at all. And if you think this is difficult, it's not. If I say SRC demo NAS parallel benchmark, okay, let me try running this application inside a container. How do I do that? I say singularity run ecp.simg. Okay, and once I'm in the container, I will go and run this application. I simply say time mpi run -np4 lu.w.4. Okay. Just a second. No such file. Yes, of course. I need to go to the directory, which is demo src demo npb 3.1 bin. In the bin directory, I have this lu.w.4. I can say time mpi run lu.w.4. Sorry, I missed the argument mpi run -np4 lu.w.4. Here it ran this. It took 1.456 seconds. Now let me just go here again and do a make clean. MPICC, I'm outside the container. I'm using SPAC load or say module load mpage. SPAC find mpage. There are two mpage. I can say SPAC find -dl mpage. And I want to pick one of the mpage, say this one. So I'll say SPAC load and then this. So now I have MPICC in my path. I'm outside the container. I can say make clean, make sweet, and I'm compiling the same application with MPI outside the container. Okay, let's see if there's a degradation. I go to the bin directory, I say time MPI run -np4 lu.w.4, and it runs the application. And look at that. It took 2.82 seconds on the host OS, and it took 1.4 seconds inside the container, right? So the E4S container was actually faster than running it on the host. I'm the only user on this machine. I hope nobody logged into this Tude 001 while I was doing this. And you can see that it ran in 1.456 seconds inside the container in Singularity. And it took 2.8 to 3 seconds on the bare metal. Can I run it again? Sure, here I run it again. Okay, this time it ran it in 1.57. It still was faster to run it in the container. Did I answer this question? Is it okay?
Oh, yes.
Yeah. So I don't see degradation in this case with the E4S container. Now we are at 8:38. I would like us to take a few minutes break and then have David continue with the actual Pantheon demo. And I hope you are all able to catch up with this hands-on session and that it's not too complex. I hope you are able to just run these commands and see exactly how this replacement of MPI takes place, how to build the containers. And then this is the Pantheon demo that we'll continue. And then finally, we will do the demo of naluwind, and then also look at the talk of Nalu. So with this, we'll take a break. Let us come back. It's 8:39 a.m. How about we take a 10-minute break and start again at 8:50 a.m. Pacific time. Is that okay?
Okay, thank you.
Yeah.
And then David can set up with his instance. I'll stop my share right now. David, is that okay? That's a very good question. I have a question here which says, will the VM instances and tutorial materials be available for a while after the ECP meetings? The answer is the VM instances will be brought down, but the beauty of this AMI is that you can go and launch your own instance and get the same environment that we have. Well, how do you do that? You go to the E4S.io webpage. That's the starting point for all of this. And then you go to the download link over here, although with EC2, you're not downloading per se. And then here is the AWS section. It says this release is available on AWS as this AMI in the US West to Oregon region. So if you had your account on AWS, an EC2 account, you could just as easily sign in, find the AMI by searching for this tag, and then you will be able to launch this. You will get the same super container. I mean, you'll get the IP address instead of the super containers. But with that IP address, you'll be able to use the 8443 E4S, log in with HPC Linux 1.2 exclamation, this tutorial, and then you will have the same instance. You'll have these slides available there. Everything will be available for you to use. Of course, it will use your account and your, it's not that expensive. You may be able to even boot up a beefier instance. I hope I answered that question. Sure, thanks. So just remember, go to the E4S.io webpage as the starting point, and then go to this AWS section to get this. We will be using this image again for the containers, intro to containers for HPC. So if you are familiar with this, you're happy to use this, the same workflow will be available for the next containers tutorial. And if you would like to use this image and want AWS access to this image, please just email me. I will bring up an instance for you, keep it running for you for the duration that you want to use it, and you can use this E4S instance. You know where to reach me. On the homepage, you'll be able to see my email right here. Just send me a note. I will bring up an AWS instance for you. How does that sound? And thank you. I'll stop the share so David can take over. David?
Yes.
Do you want to share your screen?
Sure. Let me get set up here. Just is that working?
Yeah, I can see it perfect.
And Samir, you want me to take about 30 minutes?
Well, it's 8:50 a.m. Pacific time. I would like to welcome David Rogers from Los Alamos National Laboratory to show the next Pantheon session for the next half hour. David,
Thank you.
please.
So to get started in here, all the instructions that you're gonna that we're gonna go over here are available in the virtual machine, and you can get this web page by typing Pantheon in a shell. So to follow along and get the and it's the same thing as Samir had. You know, the demo the tutorial is cut and paste, and so if you follow along, it should be pretty easy to just kind of get this stuff up and running. So yeah, if you type Pantheon, would you mind putting that in the chat for me, Samir? So if you just type the word Pantheon in a shell, you'll get this. You'll get this up, and that's how you get access to the tutorial. Okay. All right. So today, what I'm going to talk to you about is the Pantheon project, and the goals of this part of the tutorial are to provide you an overall understanding of what the Pantheon project is, show a workflow from Pantheon that's designed to run on Summit, and then provide a hands-on example of that workflow adapted to run in the tutorial VM. So we're going to run the workflow, change files, and rerun the workflow. And the reason, you know, what I want to do, or why we want to do that, is to show you kind of how you can pick apart a Pantheon workflow and adapt it and change it for what for what you might want to do to it. Okay. Real briefly, the way that this tutorial and this web page is set up is, there's two types of code here. One is this kind of gray box, and that's just kind of an example. This darker gray box with the green line is to be cut and pasted into the shell. So those are the commands that you actually want to run. And there is some funkiness about copying and pasting from Firefox and the shell. Unfortunately, they're slightly different. So if you have trouble with that, just come back to this thing, and that'll help you out. Okay, so what is Pantheon? So Pantheon, the project, is a home for examples of reproducible workflows for scientific computing. The name Pantheon actually comes from, if you're familiar with it, it's a collection, well, first of all, it's a temple dedicated to all the gods, but colloquially, the way we're using it is in this fourth definition, where it's a group of notable persons or things. So it's a group of examples is how we think about Pantheon as a project. It's a group of examples that everybody can kind of look at. So we have a couple of terms in the Pantheon project. So a project is actually a collection of workflows with a well-defined scope and goal, and they're defined by a common workflow template. A template is a workflow pattern, and a workflow is a reproducible set of operations based on that template. And when you publish one, it's defined by a URL to a Git repo and a specific Git commit. We're going to look at a project, a Pantheon project, which is part of Cinema E4S collaboration. So we've done some work with E4S to embody these workflows in a way that takes advantage of both SPAC and E4S. Staying at a high level, why are we talking about Pantheon in the context of this tutorial? So Samir showed you an incredible amount of capability that's available for you to take advantage of, to run, to set up environments and run things. Pantheon really is something that takes advantage of all of these things and then runs examples of these things. So, at a high level, we take advantage of everything that E4S and SPAC and all these other ECP capabilities have out there to give you examples of, what would you run if you could set up one of these things that that Samir was talking to you about today. Well, here are examples of things that you might want to run. Okay. A Pantheon workflow can be in any one of a couple of states. So we talk about a release workflow if it's supported and expected to work. These are the ones that we're working on now in Pantheon because we want people to be able to kind of go to these repositories, pull them, and have them work. So we're working on release workflows. The concept of a development one is one where, hey, we're working on this workflow and we'd actually like people to use it. We like it to be supported, but it's not quite there yet. And then you can have an experimental workflow, which is, hey, here's something that works. It's probably a good thing to have out there for people to see, but we're not going to support it, and it's really kind of finicky, but gosh, it's a great example for people to see. So that would be an experimental workflow. There's a little bit of metadata that we define, and this, we can go into more detail about this on the Pantheon project page, but you can think of a Pantheon workflow as a kind of an entry in this big database of workflows that we've got, and we just need a few things to keep track of exactly what workflow you've got there. So let me show you. So the Pantheon website, so pantheonscience.org, has a lot of this high-level information. It also has links to the projects, and in particular, this Cinema E4S collaboration that I'm talking about today. So this has that information that I talked about. It has a high-level description of what the project is about. So in this case, we're talking about workflows that specifically embody use cases for analysis and visualization that are that use the Cinema capability in ECP. And the scope and goals are here as well. You can look through. There's the workflows that are released are actually here, and you can click through on this and take a look at the web pages for these workflows. These have diagrams and examples and more instructions if you want to go and look at those. And these you should be able to download and run on Summit. So in the background, if you're kind of bored with what I'm presenting, if you want to log in on Summit, pull these repositories at this commit, you should be able to just execute these on Summit as well. Okay. So let's see here. So what are we going to do today? We're going to look at an example of a Pantheon workflow, which uses this mini scientific application Cloverleaf, creates a Cinnamon database in situ using the Ascent infrastructure. And this is kind of a, a through line of all the kind of stuff that we're working with in the ECP analysis and visualization capabilities. So looking at this diagram, the Cloverleaf simulation is is coupled with the Ascent infrastructure, and it's going to use that to create a visualization and write out a Cinnamon database on disk. And then we'll package it up, put a viewer in it, and I'll let you look at it. So here's where you start having to swipe if you're gonna play along with me here today. We need to set up a few things for the environment. So go ahead and copy and paste this into your browser or into your shell, sorry. And that's just going to set a few things up in the environment. If you want to take a look at the things that we're going to be produce here, copy and paste the next thing. Whoops, see, I did it wrong. Which will show you a Jupyter notebook of the resulting Cinema database. And so this will bring up the database in your browser, and you can, scroll through time and kind of look at this simulation here. We'll go through and fill out some more of these things, but basically, this gives you an example of kind of what we're looking at the end for today. So you can also bring this up in Firefox if you'd like, and that's the command to do that. Okay, so that's the end result of what we're going to do. So let's take a look at the workflow, because this is the kind of part of the contribution of the Pantheon project is breaking things down into these little bits. So if you CD into the tutorial shell or directory, there you go. And typically you have to kind of, whoops. Did I do that wrong? Got to get rid of my Python notebook here. Okay, so I'm going to CD into that directory. Nope, not well. All right, so let's look at what's in there. Let's say that you wanted to run one of these. You went to the Pantheon website and pulled the workflow at the commit that's on there. You're going to see a bunch of files, and the philosophy behind this is that you should be able to kind of dig in here, and if you're somewhat experienced in programming, which we assume you are because you're working with HPC, and how else would you get anything done? You're going to come in here, and this should be a well-organized set of files that you can look at and explore yourself without a whole lot of extra documentation. And what that means is that, that puts the burden on the person creating the workflow to spell things out well, but we've also kind of broken things down into the structure of this template so that you should be able to get around by just looking at the files. The first file to look at is the execute script. And this is the thing when you pull one of these workflows and you get it set up, you just type execute and the thing should run. It should do all the steps in the execute script and run successfully. What are these steps? Well, there's a setup step where you might install things if you need to. Run the workflow application on a high performance computing machine. You got to wait for the completion of that run. And there's a little bit of script in there that helps you do that interactively in the shell. In fact, let me, well, it's okay. We process the results, wait for the completion of that, and then validate. And so those are the steps that you see if we were running this on a high performance computing infrastructure. So we have adapted this actually for this tutorial. well, let me show you. I want to show you one thing here. So if we were to just run this thing on a supercomputer, you type execute and the thing would go off. It installs things, and we use SPAC underneath things for all the reasons that Samir was talking about this morning. It encapsulates things nicely. It allows us to do things like utilize the caches that Samir was talking about. And this is showing you that on Summit. This is actually running on Summit. This is a video that I took. But once we get to the point where we're installing things, the magical thing about what the infrastructure that Samir has been talking about is that instead of building all this stuff now, we can go out, access these caches, and it pulls them in, and it really, really, really improves the runtime of running one of these workflows. So instead of having this big long delay where you're actually building everything, going out and getting the cache speed things up, by at least an order of magnitude. So that's what's happening here in this script. You submit the run, and then you wait for the run to complete. And then at the end, the workflow will verify that things have gone the way that you wanted to. So this is what it would look like if you were running it on Summit. So it'll be slightly different running it on this machine, but not a whole lot. So if we look at an overview of the steps, so if you in the install portion of the script, this creates a work area. It installs SPAC if needed at a specific commit. So we've frozen, what's going to be installed, and we can manage that. So this is why we can actually say, hey, this thing could be a released version of the workflow, because we know we can pin the versions to things that we know are going to work. This is actually new for us in supporting this, and it's really because of the work that's been done in SPAC and E4S that it's possible to do these things, I think, in a reliable way. The install script will install dependencies, and this is where we get that big speed up in performance by using the E4S cache. And boy, when you take these things from, this is a simple example, but when you take these things to the applications and the dependency tree gets really big, like Samir was showing, this step can be quite long in the build process. And I love that diagram that Samir showed before at the beginning of the talk, which was, this is how you build things on an HPC system. We've all been through that. And, so really from a Pantheon perspective, the E4S cache and SPAC take this from something where, somebody might try this once because the build step is so long, to something that you could try, many times in 1 hour, because this thing is just so fast. So the run script creates, the run directory, copies files it needs to and submits the job. And the post process in the case that we're going to see today, installs cinema viewers alongside the databases, packages them up, and then, so that you could SCP them to a local machine if you'd like. And then the validate checks the output to make sure that it actually ran correctly and then reports that to you. So this is all the kind of stuff that you would typically, that's what you expect in a workflow. So I guess the one thing to note here is the way this is constructed and pulled apart in this way, so that you can use this workflow as a kind of example to start your own work. So if you take this example that we showed today and you wanted to try some new things, or you had an idea about, or you wanted to, maybe learn about how the simulation ran, kind of what the input files did and things like that. Once you're done with the install step, you can just keep rerunning the run step. And this is the kind of thing we're going to do today. You can change things, you can look at it. It really gives you the ability to just kind of play around with it. And that's one of the reasons that we wanted to do this set of examples, is so that people could, take Nix or take another application and say, I'd like to kind of know how that runs. How do I get it working? And, these can serve as examples for that. And you do that by just running these individual steps by themselves. So the execute script is really just a simplified wrapper that both enumerates the steps and then does them one by one. But you can run any one of these after changing things yourself. Okay. That, you might break it, but you can always check out the repository again and or check out the files that you've changed and get it back to a working state. Okay, so it's a place to do experiments. So the example that we have today, basically we started with one that ran on Summit. Installed in this virtual machine is SPAC and is the mini app and Ascent and things like that. So basically, the nice thing about actually the way this is structured is if you look at the run script, so I'll go back to the previous one. You can actually look at these in the tutorial. Oops, can I grab that? Having trouble.
Population reduction.
All right. Anyway, so in this run script, you can see the first thing that it does is it uses SPAC to actually find where things are installed. So regardless of how you set it up, if you just use this run script, it's going to find that and then run things. Okay, so you can adapt that to use on your supercomputer. We can do it here in the virtual machine as well. So that's what we did. So we just, for the purposes of this tutorial, we just skip that step. Okay, so if you cd into the Pantheon tutorial directory, and run execute, this workflow will run. So it'll set up the build, it'll set up the results area. It's going to go ahead and do the run. And this is the output from Cloverleaf 3D that you're seeing. It's pausing every 10 time steps to write out the data into the Cinema database. So that's the behavior you're seeing. And then it finishes up and checks. And you can see here that it passed the validation step. Okay, so you can look at the results. And I'll do that here. And so this is a slightly different viewer than I showed you before. This is simply one that's written in JavaScript, but this shows you the results from that, the output of that simulation. I'll get rid of some of these windows here. Okay, so that's what happens if you simply, whoops. That's the behavior you get if you simply run the execute script as it's done now. I want to show you a little bit of how you might go about picking this apart and doing some of your own exploration. So there's a bunch of files sitting in here that we copy around and use to run the simulation, and also define the visualization that you get in the Cinema database. So we're going to take a look at those and change them and see what happens. So typically, the way that we have these structured, there is a inputs directory. And so if we look at that inputs directory, we have a subdirectory per application here. So there's a Cloverleaf set, there's Cloverleaf inputs, there's stuff for SPAC, etc. So you would expect that if I'm running Cloverleaf, that I would want to change the input file that defines the behavior for Cloverleaf. So that's what we do. If we look at this input file, it's in inputs Cloverleaf clover in. And one of the things that's easy to do without breaking it is to change this end step. So this will change the number of time steps you've got. Okay, so if we do that, so if I'm going to change this to 100, just, whoops. Okay, so now we've set it up so that it's going to run for 100 time steps. One of the other things that you can do, So Ascent is a really full-featured kind of infrastructure for both analysis and visualization. And its behavior is defined by a file called Ascent Actions. We can look at that thing. It's basically a YAML file that defines the kind of visualization you want to do, the kind of views that you want to get out of it. Down at the bottom of this page is actually what that looks like. So what we're going to do is we're going to change this Ascent Actions file. There's two examples in this tutorial. So if you copy, there's the original one that we have here on the left is a volume rendering, and it's pretty easy to change that over to an isosurface visualization. And I did this by just looking at the examples that are in the Ascent documentation and then copying and kind of monkeying around with it until it worked. So if we want to change the visualization, all we have to do is change that the Ascent.yaml file that's being used by the workflow. So go ahead and do that. And there's two versions of this in that directory. You can kind of flip them back and forth by copying them over the Ascent.actions file. If you'd like, you can alter things like phi and theta. In this defines the kind of views that you get out from the Cinema database at the end. So you can kind of monkey around with those and make more views. The thing with the demo here is that kind of takes up a little more time, so I'm not going to go into that right now, but you can play with that. Now, if we run the workflow and we look at the results, so we've changed the number of time steps and we've changed the type of visualization that we're going to get. And we type execute. Same thing happens. It's going to every 20th or every 10th time step, it's going to pause and output a Cinema database or an entry into the Cinema database. So this runs for 100 time steps. Okay, and then it does the same thing. It packages up the database for you and validates that it ran. So let's look at the results here. Okay, so here's the different visualization that you get from running it that way. You can see that we got an isosurface rather than the volume visualization that we had before. And there's a few different views of that you can look through. Okay, so let's see. So yeah, so wow, I got through that a little quicker than I thought. I don't know if I probably didn't leave enough time for people to try things. I apologize. But kind of the overview that I wanted to show you was that these collections of workflows that we've got and that we're publishing more of provide a way for you to both for us from the Cinema project perspective to be able to test things across the ECP stack using E4S and SPAC. It actually makes it our iteration time on these things much shorter, so we can actually use these things for development and design and things like this. So that's a critical part of making this thing actually work and be useful. Let's see, let's go back here. Oops, sorry. So yeah, these things are designed as both examples for people to kind of come and dig into and learn about how the applications work, how does the viz work, how do the elements of the workflow actually work. And I really feel like since we have this whole infrastructure now, it really makes it something that people could actually use as a learning vehicle, because as I said, if you pull these repositories and actually run them on Summit, they actually run in a very they're very short because of the cache, and so people really can kind of monkey around with these things, change the settings, and do their own exploration. So they do serve as examples for people to look at. They also serve as examples and ways for us to test, this cross ECP, cross project kind of interrelationships that we've got, because at the end where we are with cinema, we have to be able to say, can we get an example of Nix running, doing different kinds of operations and visualize that, so that it's very, that's the kind of end-to-end of what we've developed here. So, okay, so I think that's all that I have to talk about. I encourage you to dig in and take a look at these things. We are publishing more examples of these things. We have, I'd say, about a half a dozen applications right now that we're trying to get up running and get good examples out. And if you have questions, you can email me, or you can look at the Pantheon project page, and there's contact information there as well. So I guess I would take questions and see if anybody has anything they'd like to talk about. So I guess I should look at the chat. Oops. Yeah.
David, if you want to just go through the README file and cut and paste those commands for others to just follow along, they can do the Pantheon demo that way.
Oh, in the chat?
No, I mean in the actual. So I can just as easily.
Was there a URL where we could get the different pieces of this workflow? Like, is this in a repo somewhere?
Yeah, so the project, I'll put the project page here. So if you go there and click and look at the applications, it'll point you to the repositories.
I think you're not sharing anymore.
I'm not, I just put something in the chat.
In the chat.
Sorry, yeah.
Okay. Sorry.
Yeah.
I thought this was a really awesome demo.
Thanks.
So you can also try this with the README file you see over here, the demo for.
Yeah, it's down if you search for
screen,
Pantheon,
right?
yeah.
There, so you can just go to this CD tutorial. Sorry, over here. Pantheon tutorial, and here you can just look at this, source this setup like that.
Right, and if you
validating, okay, run the execute, and just cut and paste from here, so you'll be able to do these steps.
And also, if you just type Pantheon in a shell, it'll bring up that web page where you can kind of page through the.
Absolutely.
You can page through the documentation that I just went through for the tutorial.
Yeah.
I'll put that in the chat as well.
Yes, just Pantheon like this, and you should be able to launch the full web page.
Yeah, there you go.
That he showed. Yeah. Okay. So here it's running and then of course you do the push D, Jupyter, Firefox, and this final step. I hope you are all able to just follow along these directions and do this easily.
Yeah, the README has the minimal set there.
Yes, the minimal set.
Yeah, and then All right. Well, thank you.
So on. And we'll transition next. Let me just complete this as a user. And there we have it, with different time and there. So you should all be able to try these steps and even look at the Jupyter notebook. And there it is. Thank you, David. This all ran perfectly. We can see the image come up.
Yeah, thanks. And if you have trouble running it, if you're going to try it on Summit, just please email us, and we'll help you figure it out.
And here it is. You can see the time and page size. This Jupyter notebook should work. I hope everyone was able to follow along these steps, and from the README file, just cut and paste these sections in it. I hope it worked for everyone. Maybe we should take a minute and then transition to the next talk. Those of us who just joined us recently, please go to this https e4s.io/tutorial page, get an image, an EC2 instance, and then just log in like this with instructions on this web page. And then here's the login and password, and then read the README file over here. Our next talk today is by John Rood from NREL. And John, you can share the screen.
Hello, can you hear me?
Yeah, we can.
Okay, let me share. Okay, do the slides look okay?
Yes, they're perfect. Thanks.
Okay. Yeah, so I'm John Rood. I'm from NREL. I'm going to give an overview of our ExoWind project under ECP. So I'll give an overview of the project, and then I'll talk a little bit why E4S is kind of important for us in our project, and as well as SPAC. So ExoWind, which is going to be part of the tutorial. I think you're going to build naluwind in the tutorial today. So that's why we're discussing ExoWind project. So what this project is really trying to do is model wind farms. We started off trying to just model land-based wind farms, but there's been a big shift in WEDO, which is the Wind Energy Technology Office, to do offshore wind modeling. So now ExoWind has shifted to target even more complex modeling with ocean waves and things like that. So I'll talk about that. But so we're really trying to predict impacts of wakes and of turbines and how they interact with each other, and the turbulence, and how power output decreases when turbulence from another turbine interacts with the whole wind farm. So you can see that little image on the left side of all the wakes. I think this is an actual photograph of a foggy offshore farm in Denmark. So you can kind of see the wakes form in real life, as it were. So yeah, this is a very highly complex environment. So this project is pretty big. You can see all the labs that collaborate with us on this project. So NREL is leading it. Sandia's just as equal in it, and then we have people from Oak Ridge and Texas UT Austin. So yeah, supercomputers are key to us being able to model this, and there's about 40 people on this project, so it's fairly large. So we have a few applications that we develop. naluwind is going to be, I think, the application you'll build in the tutorial. So this is a fork of the Nalu code from Sandia, if anybody's familiar with that. So it really uses Trilinos underneath. and Trilinos has a lot of packages that are involved. But naluwind is an incompressible CFD code. So it does unstructured finite volume grids. Next, we have this OpenFast application in our modeling suite, and that came before ECP. That actually does whole turbine simulations. So it really is more so the focus of where the blades are at and how they're bending and what type of control system, or you can do pitch and yaw, things like that on the blades of the turbine. So that's what OpenFast really models, is more so of like controlling turbines. And we just recently, within the last year, introduced AMR wind, which is going to be our more so background solver. So this is a structured grid CFD solver. It's based on AMRX, but really the main difference between naluwind and AMR wind is AMR wind is structured, and we'll show that it's significantly faster than naluwind. So yeah, what we're trying to do with naluwind and AMR wind is when we've done it, we couple them together so that naluwind is really going to be doing the turbine. And this is a simple example of us modeling a sphere with naluwind. So you can see the unstructured grid around the sphere here is actually naluwind. And then there's a coupling that happens through another third-party library called Tioga. So we do overset meshing. So you really cut a hole out in the domain and then place the other simulation within it. So then you can see AMR wind is actually the structured, block structured background solver, basically we call it in our modeling environment. So we do this hybrid solver strategy to really make naluwind as dense as possible on the machine and really have the communication, because it's really, all these codes are communication heavy, but naluwind especially so. So we're trying to limit that to a small part of the machine and then have AMR wind run on most of the machine. And you can see in the plot over here that AMR wind is about 5 times faster in general for doing an ABL case at least. So the atmospheric boundary layer, so all the space in between the turbines. So yeah, AMR wind is really implemented to help us save time, and it runs on the GPUs. It runs in AMRX, and we're able to run on the early Frontier, so Tulip and Iris. So we can run on the Intel and AMD GPUs and NVIDIA GPUs with AMR wind. So we're all set up to do that thanks to AMRX. So here's just a little example just to show that naluwind actually, like totally models turbines. This was done between NREL and Denver Technical University, I think. Really just validating a certain megawatt scale turbine that they're using in Denmark. So this is just really to show the picture of a turbine with vortices. So there's a lot of complexities that go along with offshore modeling that all our codes together are trying to tackle, that you can see in this list here. So that, like the structures, this is like we even do fluid structure interactions. So the turbine has to bend according to the wind forces on it. The ocean has waves. There's atmospheric effects, and just a lot of things going on. So in the ExoWind vision that we have, and I was talking about this, most of this talk, but so naluwind's going to be around the turbine, doing all the various complicated physics there in the unstructured mesh. And then AMR wind will do a 2-phase flow solve somewhat further off of the turbine with air and water. So AMR wind will also do water effects, and I'll show you some movies of that. We have capability for that. And then further on that, along in this gray box, AMR wind will do a 1-phase solve. Yeah, I guess the coupling is really kind of in 3 levels there, according to this photo. And then OpenFast does the controlling for, pitch and yaw and stuff in the turbine. And then we have Tioga doing the actual like hole cutting in the domain to overset each application. So it gets kind of complicated. Here's some movies of the current capability that we have. So AMR wind can do atmosphere and water. So it's doing volume of fluid over in these left two movies. So here we're showing waves, and there's a dam break on the upper left. And then in the past couple of months, we've just been running this actual like full capability of naluwind's actually doing the turbine here. You can't really see where it transitions into AMR wind on this movie over here, but naluwind is very close to just the turbine, and AMR wind is the whole rest of the domain. So we're pretty confident we have that coupling working, which is pretty great for the projects. So these are all complicated applications, but naluwind is especially complicated to build. And here I have and so this is where E4S and SPAC come in. So ever since ECP started, we put Nalu and naluwind into SPAC immediately so that we could build this thing on all the different machines that we have to use, like Summit and all these other large machines at A&L and NERSC everywhere. So I forget how many packages are in this, but we even, I kind of cheat a little bit here. We have ParaView, but we were using Catalyst inside naluwind, so we can do in situ visualization with naluwind. But when you really turn on all the options, it gets to be a lot of packages. So we have in the Exowind stack, we have, I think, all the software for Exowind in SPAC. And I think I have this, can't see that. A floating window. Okay. So yeah, there's expect about a 2-hour build time on, we have a test machine that's 32 cores of Haswell. Even with an SSD, you're kind of at a minimum 2-hour build time to get to a working build of naluwind. And I find and I don't have exact numbers on this, but it's around 4 hours or more if you just show up on a login node on a system like Summit and build naluwind with a shared file system and shared nodes. So even with doing a regular SPAC install command and just letting it go, you're waiting about 4 hours or more. But our AMR wind build is pretty trivial. But we're thankful for SPAC and E4S to help our build times out, because whenever we have a new team member come on and we have to have them introduce them to the whole software stack, it's been a huge savior. Rather than doing this stuff all manually, we would never get anything done. So there's a tutorial that you're going to do that we're going to use a regression test to run in naluwind. And here's just a little overview of like what's actually running in that. So we don't have a whole lot of visually interesting regression tests, but this will do a fluid mixing on you can see it's a really odd structured mesh. And there's really on the left side, there'll just be a couple time steps where there's already a fluid in this plate, and another one will be injected on the left side. So it's just a little inflow. And this is like 90,000 elements. Yeah, and it's really just the most visually interesting regression test we have. And you can see it's fully unstructured. So that's really all I have, just to give a little overview before the tutorial. Here's another little simulation we have. You can read the credits, but if anybody has any questions, I'm open to try to answer them. And I don't know everything. I'm just a developer on this application or on this project. So there's 40 other people that have a lot more expertise than I do, but I'll try to answer any questions that anybody has on the project.
Thank you very much, John. Are there any questions for our speaker before we show the demo?
Well, I was just wondering if anyone's tried to build naluwind with multiple SPAC installs, SPAC install across multiple processes.
I do that not just for naluwind, like I guess I do that on the cluster we have at NREL. I've done, I just do a bash loop and background a bunch of SPAC install.
And is that where oh, sorry.
I've done that, but I haven't done it for just naluwind.
Ah, okay. I was just wondering if that's part of where you came up with the 2 hours.
Oh, no, that was just a regular. So that's like doing a make-J32 for every sub package. It wasn't for doing like parallelization on the SPAC install level. Does that make sense? So every package is serial
Yes.
in the DAG, but within each package, it's make-J30.
Yeah, I think if you use a recent version of SPAC, then you could get a lot more speed up out of that because you could just do
Yeah,
SPAC.
I'm curious to try it. Try more of that. I haven't done a whole lot of it yet. Okay, any other questions? All right, well, maybe I'll let the tutorial get started. Or
Okay,
if there's any
thank you. If you stop your screen share,
Yeah.
I'll start mine.
Okay.
Okay, so here, I'm back to my instructions here. I have the README file here, and we'll move on to the naluwind application. So let me start off with a clean slate. You know, if I say SPAC uninstall naluwind, okay, and it says, do you want to delete this? And let me bravely say yes. And it deleted it. So I don't have naluwind at all. SPAC find naluwind should show me that it does not exist. No package. Now let me just go to the naluwind demo. And here is where it gets interesting. I have a spac.yaml file that I described earlier. And here in this file, you can see Trilinos version. You can see the things we are installing with FFTW, with Hyper, and the full manifest of which compilers to use, which MPI to use. Everything is described in this spac.yaml file. Now, this is an environment, and I can say spac-e, pick up the environment from the current directory. So spac-e dot install. And I have configured the build cache. Okay, so when I say spac-e dot install, it will now look for all the packages. It will look at the build cache, and it found it. And this is the /build cache where it's downloading the packages from. So if you were looking for the build cache, there are many different packages over here. You can see all of these packages from the E4S build cache, and it will install the naluwind binary in my path, and then I will be able to run the next part of the demo. And there it is. It extracted it from the build cache. And now I can say SPAC find naluwind, and it should find it. There it is. So here is the demo.sh within the naluwind demo directory. This is important, just cd to this directory, cat the demo.sh. And there you can just say demo.sh. Now I have a demo where I can use the uninstrumented binary, or I can run it with tau, the tau performance system, and measure the performance. Now you can see it's starting from a blank directory. It has just a YAML file, and then there's a run script with or without tau, and it's going to run this. Yes, we are going to actually run the ECP naluwind application on this EC2 instance. Now, it takes a few minutes. It might take about 2 to 3 minutes to run this. But you can have a look at what is there in this demo file, a demo directory. Here, I'm going to the demo directory, naluwind demo, and then within that, this directory. Let me just increase the font size. And here is run.sh. You can see I delete all the output files. I run it on 8 course with this YAML file as input. Then I do a pass-fail check with the gold output to see if the results were correct. And then I merge the outputs, the 8 different outputs from the 8 ranks, to create a single merged output.e file, which contains the results of the simulation. So I'm starting out with a blank slate. I just load everything from SPAC. So SPAC is the key technology that's used for this whole deployment. And now if I want to run it with Tau, how is the workflow any different? You see, here is how I run the application with MPI run-np8 nalux. If I wanted to use Tau, I just simply say MPI run with Tau exec-EBS. EBS stands for event-based sampling. So I sample the execution periodically. So instead of this, I'm just saying this. And with no change to the binary or the build system or the source code, I will generate the performance data. You can see this is the result of the output. It ran properly, inputs. Here is the information and everything looks good. Okay. With this, I'm now able to run the output through Tau. So there are 2 things I can do. First is I can just look at the performance profile by saying paraprof like this. And the Tau profile.xml, the file that's generated by using Tau exec-EBS, will load up the GUI tools for looking at the performance data from the application. And we'll also look at the output from ParaView. Oh, wait a minute. Sorry, here is the demo.sh. I'm in the wrong folder. I need to go to the actual directory where this run was conducted. And that's where I should see 2 files, output.e and tauprofile.xml. So here I can say paraprof tauprofile.xml in the directory where we ran the code. And there it is. Now it shows me that there were 8 ranks. If I right click here, I can see many different types of windows. I'll choose the thread statistics table. What did I do? I just went over to a particular node. I right clicked and I say, show me the thread statistics table. Now here it says that the application ran in 90 seconds. The .tau application is a top level timer. And I can expand or contract this to see what's going on. Now Tau supports the Cocos profiling interface. So whatever kernel name you specify in the application in the Cocos parallel for as the first parameter, that finds its way automatically into your profile file, and you can get precise timing results for that. So you can sort the inclusive or exclusive time spent in each of those calls. Here is like bellows, sudo, block, gmrest. This is nalu, mulu, preconditioner setup. Now, this is interesting because the designer or the developer of this framework has given a meaningful name over here. When the meaningful name is not given as the first argument, you can see the default name, which is still useful, which says parallel for Sierra Nalu assemble edge solver algorithm. But here you can actually go down and look at the bellows operations and see even down to the level of statements. Let me just pick this parallel for Nalu loop. Here it says spending about 2.7 seconds over here. Here is a function called Sierra Nalu momentum edge solver alg execute. If I open this, there are several samples. I can say, show me the function bar chart, and it shows me the full template instantiation right down to where this was taking time. It shows me the file name also the line number. I could just as easily right click and say, show me the source code. And then it will launch the source browser and show me the exact line of code in this for loop where the application spent its time in that location. So I can see at the COCOS level, I can see at the MPI level, I can see at the algorithm level, at the statement line number, where the application is spending time on which CPUs, how much time is spent, and a complete breakdown. This can be very useful in looking at these names where the user has specified these names, and without any modification to the binary, those names just trickle into the tau interface through COCOS. If you want to see what every rank was doing, you can look at the 3D visualization as well. And here you can see the bar plot for each rank. I can expand this. I can see over here, I can rotate this in real time. I can see exactly what each thread was doing. I can even take the function and thread slider and move it so that I can see exactly the intersection of those functions, and scatter plots, topology plots, bar plots, triangle mesh, and see the shape of the execution. Sometimes the shape can be very useful. For example, if I were in my demo directory, src demo directory, and I had a paraprof, say demo.ppk. Here is another example of the profile. So instead of looking at just a single Gantt chart for a given node, I can just go and say 3D visualization, and it can show me what every rank was doing for every thread of execution. And it shows you the shape. Now this helps me identify, for example, over here, that there are two parts to the machine. This function is the inverse of that function. There was one thread that was doing something special that was different from the rest. And look at the intersection of the function and the actual thread to determine how much time was spent at a given point. Like I can just zoom in like this and say, okay, well, this is the loop and this is the thread ID where it was taking 129 seconds in this tokamak reactor. And then zoom into this, I can look at a scatter plot and see that if I plot the minima to maxima for every function, then each rank has a unique space, unique location in this minima to maxima. So here, for example, MPI barrier takes anywhere from 31 seconds to 260 seconds. Or this function, sigma d CQL 3D, takes from 0 to 365 seconds. And I can look at the color as well. And I see that there is one thread that does something different from all the rest. And that there is a general negative correlation between these two functions, between sigma d CQL 3D and MPI barrier. So I can look at the performance data, view it, and see the bar plots in the 3D view in paraprof. So this is just an example of a data set. We looked at the data set over here. Now, with this, we are able to see the performance data. What about the actual output of this application, naluwind? And we created the output.e file here. Now, if I have paraview in my directory, I can say paraview output.e. And here is the description of that. And if you look at your slides at the end, here is the slide deck. You will find that we have, okay, here's paraview. Here's the description that John showed. What I do is I click on this output.e. Let me pick a mixture fraction. This is a mixture fraction. I click on output, mixture fraction, and click apply. Once I apply, I can now pick over here the mixture fraction that I had checked. And here is the mixture fraction. Let me click surface with edges. In fact, I can expand this. This is a 3D view. You can see the full edge. There are 90,000 elements, like John mentioned. And there's already some fluid here. I'm injecting another fluid from this edge. Let me just click on play and see the result. So you can see this fluid injected and how it's being simulated. There are many different views in ParaView. Please explore this. This is a point Gaussian view, and I can see all the elements over here. And view this. So this is a real simulation of a ECP application that we are able to run and view the results, both performance data as well as the simulation results over here. Here's the surface. And you can see the mixing over there. So with that, we have the ParaView demo. Again, what you need to do to launch this is, as the instructions say, cd to that directory and then say ParaView output.e, and then click this mixture fraction, click apply with the output, and then pick this mixture fraction from this list, and then surface or surface with edges, and then click the play button. So you can see the mixing. And I hope you are able to visualize this in 3D and use the tools. Of course, our project has made sure that all of these packages work well together, and that you have a consistent environment where you can easily launch these tools. If you are trying to build any of these tools from a scratch, it can be cumbersome at times to get all the pieces correctly. But with the help of SPAC, we are able to create a workflow. We are able to create binary build caches from E4S, and we are able to integrate a full environment which works well, whether it is the 3D browsers or so you can be immediately productive with this. So with that, let me just recap. This is the naluwind demo, and I did the ParaView output.e and did that. And here I also did paraprof tau profile.xml, right-clicked on node 0, show thread statistics table. We did the Windows 3D visualization, and then exit from there. So I'll just take a few minutes and make sure that you are able to do this. The steps are right here. We just first uninstall the naluwind. We find this, it's gone. I cd to this directory, spac-e install. Then do a demo.sh, let it run for 2-3 minutes. cd to that directory, look at how the tau exec was used. Then launch ParaView with output.e, launch paraprof. So I'll take a few minutes, and before we go on to the last part of the tutorial, which is to look at the AI ML packages that are integrated, so you can run, say, TensorFlow or PyTorch, and those who want to go ahead, please go ahead and do these steps and look at these files. I'll just wait for a few minutes for everyone to catch up and try these examples. Is that okay? Please try, just cut and paste these steps exactly like this, and you'll be able to launch this. And with ParaView, as I said, with the output.e mixture fraction, click mixture fraction here, pick these surface or other here. This is the VTK composite index. And then I'm just looking at the surface with edges. John, would you like to add anything to this demo?
I think John dropped off.
Oh, he did. Okay. Well, do you have any questions for me? I hope you are able to do this and all the 3D tools work properly in your environment. Todd says, it looks like something bad is happening to that windmill. Well, in this case, of course, we are just looking at the fluids mixing on this plate over here. But here, and if you were not able to run this for some reason, you just want to skip to the output, you can still do that. These files should be there in the directory if you didn't run the demo.sh. But it should be okay. I think in 2 minutes it completes. Can someone in the audience confirm that these steps worked okay for them? It worked. Oh, good. Just wait for another minute or so for everyone to try this. The software that's being used to render all this is the DCV from AWS, where we have built the image around that. And it seems to be working well for all our 3D examples so far. Any comments so far on the tutorial before I go to the next step? Let's just take another minute for people to try these tools. Okay. For the final step, I mentioned that E4S has integration with AI ML tools as well, and we are exploring this in the context of many different runtimes. I
have support for Intel One API, and I'll just show the One API over here now. I hope you can hear me properly. Here is the module load Intel. So I have Intel One API over here. I'll speak up a little louder. I hope this is okay. So I have support for Intel One API. I'm just going to use the conda activate PyTorch and just go to this src demo Python tests directory. And this is a simple example which uses PyTorch. And I can see that there's an import torch. And I can say Python, say which Python, Python f2.py, and it will have the PyTorch. We have conda activate TensorFlow, and then the f3.py, which is based on TensorFlow. And here is the f3.py. Here is a simple example with TensorFlow and Keras. And I can say conda activate TensorFlow and say Python f3.py. And it will run this TensorFlow example. Now, while it's doing this, let me just also mention that there is a SPAC tutorial all day on Friday. Please plan to attend that. It's a full day tutorial using SPAC to accelerate developer workflows. And you can see the URL for the SPAC tutorial, which is right here. And if I go to Firefox, this is the tutorial URL. It uses an image for doing this tutorial, and that image is available in our instance here. So when I say Docker images, you see this SPAC tutorial image, and to launch it, we just use the same kind of Docker commands and say Docker run --rm--it SPAC/tutorial latest. And then you can follow along with the tutorial with all the SPAC commands right here. The image has the SPAC tutorial. So you can use this if you didn't want to install Docker yourself on your local machines. And here is the 782 PyTorch execution. It's running. And there it is. We have optimized processor optimized version of TensorFlow, PyTorch. So you can think of E4S as this this framework that provides not just the HPC tools, but also well-integrated AI ML tools that you can use. And we have the container images, we have recipes, we have the build cache. And let's look at our goals for today. We said we'll take an AWS instance, log in, we'll run the hello numerical world. I hope you were all able to run this. We'll see the visit for visualization, the containers for HPC with Docker, Singularity, Shifter, MPI builds. We ran the NAS parallel benchmark, LU example, the Zoltan example, even replaced the MPI with Intel MPI. We ran the Pantheon demo, the naluwind demo, where we used the build cache. We showed the tau performance system using the Cocos interface for profiling. We saw the results with ParaView, the container images on Docker Hub E4S website of these products, AI ML integration with Intel One API, with PyTorch and TensorFlow, and pointers to these other tutorials. I think we have finished all of these steps with time to spare. We are at 10:09 instead of 10:30. So I would like to open it up for questions, and I would love to hear what worked, what didn't work, if there were any issues with the instructions that we put over here. If we have time here, and I will keep these instances running for another hour and a half so that you can continue to use this if you would like. And then you can, of course, always go to our e4s.io webpage, where you can find the AWS link and launch your own instance with this AMI, which is based in US West 2 Oregon region. So please feel free to chime in. Can somebody tell me what worked or didn't work? Well, thank you, Mike. Any comments from audience? Oh, thank you, Addy. Instance and README really helped to follow along. Addy, were you able to launch the ParaView visualizer? Were you able to render it in 3D properly without any delays?
Yeah, I was. I was actually able to follow along almost all steps. I think I might have missed the first one with Visit, but the ParaView and ParaProf, they worked just fine. It was great.
Great. And were you also able to use the run the Pantheon demo with the Jupyter notebooks?
So I think I skipped that part because I stepped out for a second, but if you are going to keep the instances up, I might go back and try that.
Yes, please do. We'll keep it on for another hour and a half. And if you ever need this instance to be brought up, I have funds in the AWS account, thanks to the generosity of AWS. So I can always bring up an instance that you would like with this image AMI ID. Just send me an email, or I'm available on Slack in the ECP, DM. Just anyone who wants to have this E4S image brought up on AWS, please send me a note and I'll bring it up for you.
Thanks, Samir.
Any other comments? Did things work? Were there any issues with latency or networking or anything else? Because these were quite a few things we wanted to cover in this half a day tutorial. I'm glad we could get all of these things working. But we are always trying to improve our tutorials, and if there are things that you would like to see or things that didn't work, please let us know. And even later, you can send us a note and please let us know how we can improve. I got ParaView to load and see what I think is the initial image, but I didn't get the animation to load. Okay, well, Jamie, if you go to the ParaView, do one thing, click on this mixture fraction. This should be checked when you click the apply with output. And then in this drop box, can you please pick mixture fraction over here? And then here you can say surface with edges and then press the play button. Does it work now with that? With this checked, mixture fraction selected here, and then surface with edges or point Gaussian, and here you can see the execution. Does that work for you now, Jenny? You can unmute and that got it. Okay, good. Any other questions? Did anyone else have any issues with this simulation? We wanted to show it from a scratch so that you get the binary from the E4S build cache, you run it with no output files initially, and then it creates all the files, you generate the performance data, you generate the output that can be visualized in ParaView, and all the pieces work together in a consistent manner. Anyone else have any difficulty with this or comments? Well, if not, I would like to thank the Exascale Computing Project for their sponsorship of this, and I would like to thank our team who have helped tremendously in making this tutorial a success. Thank you very much, and I guess we are early, so I'll stop sharing.